In our other videos regarding the root 3, we've covered roughly 90% of what you're going to see on the PE test. That's not a hard and fast percentage. Just generally speaking, the vast majority of what you're going to see is going to involve the use of the root 3 in your power calculations. But there is a small percentage of the time, once again roughly, where a new formula will come out for your power calculation that does not have a root 3 at all in it. We are going to see a power calculation which is 3VI. Now that's a unique scenario, and we're going to explore that as our final video in this series. For an example to demonstrate this, let's say we have a 3-phase source connected to a 3-phase load. For our diagram here, we're going to go from delta to Y. Let's add a current here and a phase voltage here. Let's quantify the givens. So our current I equals 45 amps, and the phase voltage equals 2.77 kilovolts. In our previous videos, we used examples where the load was single phase, but here we see that it's unique in that it's a 3-phase load. And so that presents a unique scenario for us to look at, and we already talked about we are in a unique scenario with using 3VI for our power calculation. So how do we get power with a 3-phase load? It can get confusing because we don't know which voltage or which current to use in our particular calculation. Do we use line current? Do we use line voltage, phase voltage? How exactly does all of this come together? It's a unique situation, unlike our previous examples. So a way to simplify it, actually, is to sort of break up the 3 phases into 3 single phases and model it like 3 single-phase circuits, little individual circuits. The benefit to this little trick is that we can find the power very easily in one of the individual phases, and then as soon as we have that power value, we just really multiply by 3. Very, very simple, actually. And this is the point that a lot of engineers are going to get confused because they're going to be so ready to use that root 3. They're thinking polyphase loads, this seems like a situation that is familiar for the root 3 to be applied, and so they're going to want to whip the root 3 out in their calculations inappropriately in a particular situation like that, like this one. So when we look at this problem, we should see very clearly that with the givens, we have been given all of the necessary information to derive power at one of the phases of the load. We don't need to do any conversion. We don't need to work from line to phase to line, anything like that. We have load phase values that can give us the power per phase. And so it really becomes a simple power calculation using our voltage and current on the phases, on the phase rather given here. Once we derive our kVA per phase, then we can put it through the final step of multiplying it by 3 to derive all 3 phases quantities together for a total power at the load. Now in the end, this is really actually quite a simple process. Obviously you see here the algebra that we're doing is super, super simple. And we're not saying that this is difficult. It just can be tricky when we engineers are so ready to have this root 3 to be used for these sorts of power calculations. So really just have in your back pocket this little trick that we gave down here about breaking it up into the 3 individual phase circuits. And it really should be pretty self-explanatory for you at that point. So long as you're remembering that the root 3 is not just blanket, blindly applied to power calculations, no matter what the situation and so forth, you should be in the clear.